trigonometry, and I think you'll like today's stuff. It might be something that you're familiar with from past classes, but maybe not. As a reminder, I've put on here that sine and cosine are y over the radius, and that cosine is the x value over the radius. But we also have, instead of saying x and y, sometimes we're going to just draw some right triangles, and we can use those relationships in a little easier format. Depending upon, because as we know, our theta or our degree value isn't always in the bottom left-hand corner where it's focused around the unit circle. What if I'm talking about the top right of the triangle? We need to have a relationship there. So what if we're given a right triangle and let's say our theta is in the bottom left, but it could be in the top right as well. From the viewpoint of our degree value, this opposite side, and then there's an adjacent side, and of course the hypotenuse. If theta was in the top right-hand corner, of course, the adjacent side is now the opposite side, and then the one next to it is the adjacent side. So depending upon where it's located. Sine can be found by taking the opposite side from theta over the hypotenuse. Cosine can be taken the adjacent side over the hypotenuse, and tangent can be taken the opposite over adjacent, or the y over the x, which is kind of just a different way of looking at it. Some ways, a mnemonic that many remember this by is called SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right, let's head to slide 2, where we can actually put these relationships to order. So I'm looking at alpha. Alpha is in the bottom left-hand corner. We have a triangle. Find the value for cosine. So if SOHCAHTOA helps you, we're looking for cosine, which is opposite over adjacent. So we're looking for cosine of alpha. So from the viewpoint of alpha, adjacent over hypotenuse would be 15/17. And we'll leave it in its exact value. In example 2, we're looking for cosine of alpha, sine of alpha, cosine of beta, sine of beta. So let's start with cosine of alpha, which is adjacent over hypotenuse. So from the viewpoint of alpha, the adjacent angle or side is 3, and the hypotenuse we know is 5. Also, let's find sine of alpha. Sine of alpha is opposite over hypotenuse. The opposite side is 4, and the hypotenuse is 5. Switching viewpoints then, let's turn our attention to beta. Cosine of beta is still going to be adjacent over hypotenuse, except now the adjacent side is 4, but the hypotenuse is still 5. And sine of beta is still going to be opposite over hypotenuse, except the opposite side is 3, but the obviously hypotenuse is still 5. Take a look at sine of alpha and cosine of beta, as well as cosine of alpha, sine of beta. Noticing we're getting the exact same thing. So maybe there is something going on here that might be interesting to dive a little deeper into. Let's head to slide 3. For example 3, It says that a right triangle is drawn with an angle alpha opposite a side with length 33, angle beta opposite a side with length 56, and a hypotenuse of 65. Find sine and cosine of alpha and beta. So I'm just going to draw a right triangle. I'm going to call one side beta, or one angle beta, and one angle alpha. We know this other one has to be 90 degrees. It says that alpha is opposite the side with length 33. So alpha is opposite of side 33. And it says beta is opposite of side length 56. And that the hypotenuse is 65. So now we've found both of our side lengths and our hypotenuse. Let's find sine of alpha first. So from the viewpoint of alpha, sine is opposite over hypotenuse, or 33 over 65. And cosine of alpha is adjacent over hypotenuse, or 56 over 65. Now let's turn our attention to the viewpoint of beta. Sine of beta, still opposite over hypotenuse. Opposite is now 56 over the hypotenuse is 65. And cosine of beta is adjacent over hypotenuse, or 33 over 65. Just like the previous page, we see that there is a pattern between cosine of alpha, sine of beta, sine of alpha, cosine of beta. We just found and saw two different examples where cosine of alpha, sine of beta, and their opposites are the exact same. This is because we know we need a triangle to add to 180 degrees, which means that regardless of what the other two angles are, we would have to subtract either the alpha or the beta from 90 degrees. 90 degrees again is the same as pi over 2, which leads us to cofunction identities, sine and cosine. So cosine of beta can be found by taking sine of pi over 2, or 90 degrees minus whatever the angle is, and vice versa. And these cofunction identities are listed on your identity sheet, so you have them handy for you. They even give you cosine, sine, tangent, secant, cotangent, and cosecant. So you've got all of them listed there. Let's find an unknown side of a triangle. So let's head to slide 4 for example 4. We have a right triangle. We have a degree value. We have an opposite side of that degree value. We don't know what the hypotenuse is, and we don't know what the adjacent side is. I know the following. I know if I were to take sine of 30 degrees, sine is opposite over hypotenuse. I would have 7 over the hypotenuse. I could easily solve for b by multiplying both sides by b. So our hypotenuse would have to be 7 divided by the sine of 30 degrees. And I bet we could use our exact trig values to know that sine of 30 degrees is 1/2. And 7 divided by half is 14, since 14 halves go into 7. Now I know side length b. We can use Pythagorean's theorem. 7 squared plus a squared is 14 squared. So a is equal to the square root of 147. And noticing I'm leaving it in its exact value. So just because we use sine here, you may have wanted to use cosine. However, cosine is adjacent over hypotenuse, and we didn't have adjacent side or the hypotenuse side, which is why I chose to use sine, because I knew one of the two so that I could utilize it effectively. Let's look at example 5, where we have a right triangle that has an angle of pi over 3, and it tells us the hypotenuse. Find the other sides. Just going to draw a right triangle so I can get an idea. I'm a picture person. This is pi over 3. We know pi over 3 is the same as 60 degrees, if that's helpful for you. And it tells us the hypotenuse is 20. But we don't know the opposite side, and we don't know the adjacent side. Here you could use sine or cosine, because either one of them would give you the hypotenuse. And since we used sine last time, let's use cosine. I'm going to use cosine of 60 degrees is adjacent. Oops, we should use B for adjacent. Our adjacent side over the hypotenuse. Can multiply both sides by 20, so 20 times cosine of 60 degrees is equal to our adjacent side. Cosine of 60 degrees, using our exact trig values, we know that cosine of 60 degrees or pi over 3 is half. So 10 has to be our adjacent side length. Well, now that we know two of them, we can find the third by using Pythagorean's theorem. 10 squared plus a squared is 20 squared. 100 plus a squared is 400. A squared is 300. When I take the square root of 300, we want to simplify our radical. I know 300 is the same as 3 times 100. So I can take the square root of 100 as 10 square root 3. So side length A, or our opposite side, is 10 square root 3. All right, a couple more examples to end our day together. The real meat. So we've used sine and cosine to solve. Why not use tangent to solve? Why not use tangent to solve? So that's example 6 on slide 5. To find the height of a tree, a person walks to a point 30 feet from the base of the tree and measures the angle from the ground to the top of the tree to be 57 degrees. Let's find the height of the tree. All right, so we've got ourselves a tree here. We walked 30 feet away from the tree. We say that the angle from the ground looking up was 57 degrees. We're looking for how high is this tree. We don't know the height of this tree. So we're only given the adjacent side, but we don't know the opposite side. This is where tangent is going to come into play. We know tangent, tangent is opposite over adjacent. And we have tangent of 57 degrees, which is not a degree value that we know of. So we're going to need to use our calculator, either using Desmos and typing in tangent 57 degrees, or your TI-83 or whatever calculator, Texas Instrument calculator you have. Even your phone, your smartphone, when you tilt it on the side, you can type tangent and then the degree value in it is equal to x over 30. Multiplying both sides by 30, so 30 times tangent of 57 degrees is going to be our height value, and it's approximately 46.2 feet, or rounded to the nearest whole is 46 feet. So again, you can utilize your smartphone, just tilting it on its side if you need to. And you can see tangents, sine and cosine. If you go to decimals, you can also type it in, just tan and then the degree value. All right, the last example. A person is standing on the roof of a 100-foot building, is looking toward a skyscraper a few blocks away, wondering how tall it is. She measures the angle of declination from the roof of the building to the base of the skyscraper to be 20 degrees, and the angle of inclination to the top of the skyscraper to be 42 degrees. All right, so let's draw a little picture here, see what we're looking at. So let's say we're standing on the roof here, and we're looking at this skyscraper that is supposedly super tall. We want to know what is the height of the skyscraper. And we're looking up and we're looking down, but ultimately it's creating two separate triangles for us, two separate right triangles. Looking down, it tells us that it has a declination, so looking down is 20 degrees. But looking up, inclination is 42 degrees. We know that we're standing on a 100-foot building, so I know if I were to look over across at the skyscraper, that this side would also have to be 100 feet. But I'm only given on my top triangle, I'm only given a degree value. I'm going to need to find this length here so that I at least have a base length that I can use in order to find the other portion of the skyscraper. So we already know that a portion of the skyscraper is 100 feet. We need to know what this other height is. So we need both of these triangles to help us find some information. So I'm going to start with my bottom triangle and find this length here, the length from my person to the skyscraper itself, using tangent, because I'm looking for one of the sides when I'm given another side. So I'm going to say tangent of 20 degrees is equal to the opposite side of 100. And I'm going to call this side x, the adjacent side. Multiplying both sides by x, and then dividing. This side is going to be equal to 100 over tangent of 20 degrees. We know we're going to get a decimal, friends, so don't leave this in its exact value, will you? Don't turn this into a decimal, because then you're rounding here and you're rounding in another step. So you're rounding twice, which can affect the overall value. So this entire x value represents the adjacent side of 42 degrees. Now that we know the adjacent side, we can find this other opposite side using tangent again. So I'm going to use tangent again, except this time we have tangent of 42 degrees is equal to, we're not quite sure what the opposite side is, but we know the adjacent side was this weird piece that I said, keep it exact. We know we can multiply by the reciprocal. To get rid of that complicated fraction. Oh, I probably shouldn't do it that way. Let's back up. Let's just start a new step. So this would be equal to a times tangent of 20 degrees over 100. But this is still equal to tangent of 42 degrees. So again, I can divide both sides or multiply by the reciprocal. So A is equal to tangent of 42 degrees, multiplying by the reciprocal because I'm dividing. And we'll get an approximate answer, but this time our answer is more approximate than if we were to get a decimal here and then get a decimal through each one of our steps. And of course, that ultimately skews our ending result. So this is about 247.4 feet. So we know that over here is 247.4 feet. But altogether, the height of our skyscraper is adding them together with 347.4 feet. So even though sometimes they may not have pictures, I definitely recommend drawing the pictures. You can get an idea of what information we have and what information we need in order to move forward instead of trying to visualize it in our heads. So that is the conclusion of lesson 5.5.